Hello everyone again and welcome to machine learning tips. We did look at the linear types of supervised learning techniques. So today we will be looking at the non-linear aspect. So most of the times for most machine learning applications in real world problems, we do not really find that linear relationship between the input and the target variable. So most real-world applications in machine learning, we mostly use these non-linear techniques, which are also called non-parametric methods. So for the non-linear supervised learning methods, models are built by capturing non-linear relationship between those input features and the target, where we are not assuming any straight line or maybe strictly an additive form. Unlike the linear models like linear regression and the logistic regression we saw earlier, which assumes that linear relationship between the variables, non-linear method can capture curves, interaction thresholds, as well as more in intricate patterns in the data. So for the start, we are going to be looking at the first non-linear technique, which is a distance-based method, um, which instead of fitting a single global function, we are looking at some distance-based method, uh, which looks by storing that training data and make predictions by comparing a new point to the most similar stored points according to that distance metric. And we already saw the Euclidean distance, which I did mention. That distance measure most of us did in junior and senior secondary high school. So the first distance-based non-linear supervised learning method we will be looking at today will be what we call the k-nearest neighbor. The k-nearest neighbor is a common technique. It's pretty fast and it's used a lot for most machine learning applications. So KNN, which is mostly called, is a non-parametric approach, instance-based algorithm for both. We use this for both the supervised learning techniques like classification-based and regression. So meaning that we can use this not only for regression problems, we can use it for cases where we have different classes, like we saw, like classifying messages into spam and non-spam and so on, and also regression problems where we are trying to predict the prices of houses, as we saw earlier. So KNN uses the concept of if you are similar to your neighbors and then you are one of them. That is actually the concept that it uses. So it uses all that training data and then try to look at some neighborhood. You are going to place that neighborhood that you want. You can put this K here stands for the number of neighborhood you want. You can put K as 3, K as 2, K as 5, and so on. We are going to see how we can use the different values for choosing that K based on the kind of data set that we have. So the core idea here for KNN is giving an input future like X new, we find a K closest training samples and aggregate those their target. So KNet uses the entire training set. No training is actually required. No training is required because we are not actually trying to obtain, like in the case of a parametric form like regression, where we have to train a model to obtain the parameters and then using to do some predictions. For KNN, we are not training that model. We are just using the entire data set. And then if we pick a new point and try to make a prediction, for example, if it is a classification problem, we look at, let's say if we pick k equals to 3, we are going to calculate distances closer to that point and then look at the majority points that are really actually close to this new point we are trying to predict. And then we take it and say, okay, it belongs to this class. So for us to calculate those distances closer to this new point, for example, the common distance metric I did mention is what? Is the Euclidean distance, which is like the distance between 2 points. Other distance metric that we can use is the Manhattan distance, which is this Manhattan distance is not looking at the square difference between a point and its closest neighbor. What it does is that we are instead looking at the absolute value. We also have the cosine distance. We use this cosine similarity mostly if we have a data set that has to do with maybe text. we are going to see how we can do that, like trying to, in terms of the spam prediction, we will see most of these examples. Also, we have other distance metrics like the Hamming distance and so on. So let's look at how it does classification. So what it happens is that if we pick a point and then we pick a neighbor, let's say that point is closer to that neighbor, and then if we say that neighborhood is some k nearest, that neighborhood, we k here is just the number of neighbors we want closer to this new point we are going to pick. So when we pick this, we can find that the distances that are closer to this new point as much as possible, depending on the value of k. And then what happens for a classification-based problem is we look at the mode. Mode here simply means we are picking the majority of points that are closer to this new point, based on on the value of k. But for regression problems, we are not going to be picking that majority vote. What we are going to do is we are going to look at the average of all those points that are closer to that neighborhood. So that is how KNN works for both classification and regression problems. So one thing we have to note here that predictions are mostly made by searching the k similar instances according to a distance and summarizing those output, as I have been mentioning. The summarization of this output will now depend whether it is a regression problem. We are going to be looking at the average points that are closer to that new point we are trying to predict. And then if it is a classification problem, we are going to be looking at the majority of points that are closer to that new point. So for the value of k, the best way we can find it is by testing. Also, this algorithm is very sensitive to the cost of dimensionality, meaning that if we have a data set that the dimension is pretty high, then KNN might not be a good or best algorithm for such cases. So when do we use KNN? For classification problems, we can use it for image recognition, especially we have just small feature set like classifying digits or symbols with compact embeddings. Also, we can use it for text classification with embeddings like spam versus ham. Ham here is non-spam text using some vector embeddings in low dimensions. We are going to see how we can convert text into a vector space and then try to calculate, use KNN to actually classify whether a text is spam or non-spam. Also, we can use it for medical or risk buckets when label cases are informative locally. Also for regression problems, we can use it for price or demand estimation, like predict a product's price based on some similar items, features. We can also use it for environmental interpolation and so on. So KNN works best when the local neighborhoods are meaningful and the future space is not too high, like the cost of dimensionality as I've been mentioning. So one of the key practical aspects we should keep in mind here with KNN is that it's always good to use what we call the future scaling. Remember, if we have a data set that there is a lot of differences in between the values of those futures, and since we are using a distance metrics to actually calculate the distance between each of those futures and then try to map whether there is some, how close are these futures relative to the output we are trying to predict. Most of the times we need to scale those futures. And we have already seen different normalization techniques, which we had the standardization, which is the z-score, as well the min-max scaling. Also choosing the value of k. Most of the times, I would say when we choose value of k is so small, we are going to be having a low bias and high variance. Remember, a model that has low bias and high variance is going to overfit. So most of the times we want some value of k. Large values will lead to higher bias and lower variance, which might underfit. We have already seen all these concepts of overfitting and underfitting. So most of the time, as I mentioned, we choose values of k to be odd, which helps reduces ties in binary classification problems. Now, in binary classification problems, it will be like, even we just have like two classes with non binary. So most of the times for us to reduce this notion of overfitting and underfitting, it's always good to choose odd values for k. That is a practical example scenario that I've seen a lot, especially for KNN. And also, I will also recommend that you shouldn't choose the value of K starting from 1, because in that case, it will always work overfit. And then looking at the cost of dimensionality, since KNN doesn't work well for data set that are pretty having high dimensional space, it's always good to reduce the dimension, where we are going to see PCA or some future selection techniques as we move on along with this lesson. Also, we want to look at most algorithms want to know the complexity of that algorithm, which is is always O of n multiplied by p, where n is the training space and p is what? The number of features. And also, I did mention the notion of imbalanced class problems. We should consider weighting these, making sure that these classes are balanced before we can use what? KNN, or better still, we can use stratified sampling to actually, when we are trying to cut that data, to stratify sampling to make sure that the categories of those classes are same for each training set that we are trying to use for KNN. Also, a good technique is also to make sure that we do not have missing values, and also we are converting all categorical features into what? Into numeric. So let's just see how KNN works by using some sample diagram to see what happens. Let's say we have this diagram, which the key concept here is the distance from this new point. The new point here is this green star. So if, for example, we are trying to predict where this point belongs to, let's say we are choosing k to be equals to 3. So we will see that the points that are pretty closer to this new point, which is this green light, should be what? Should be the class, the orange class, because we have how many points belong there. If we choose k as 3, we are seeing that the majority of points that are closer to this star should be what? Should be this orange class. So we can predict that this new point belongs to what? To class 1. So that is how it works in theory. And also, another intuition, we can also look at decision boundaries for different values of k, especially for non-linear boundaries, or highly cases that are non-linear. Let's say we choose, in contrast, k equals to 1 for very flexible, and k equals to 15 for what? A smarter decision boundary. If I run this, and then we try to look at, it's still running, so yeah. So we can see here that when k is equals to 1, we have a very flexible model. And most of the time, we are seeing that we are trying to fit every point here. But in this case, that this model might perform well in during training, but during if we are trying to use a data set that the model wasn't used during the estimation of these boundaries, then this model might not be able to perform well in a real world scenario. So that is why most of the times I do not advise that we use the value of k to be equals to what? 1. So for k equals to what? 15, we can see something which is much more smoother. We see that we are not fitting every other point, but we see that that decision boundary is looking a little bit much more better compared to the case when we have what? K is equals to 1. Guys, that was it for today. Tomorrow we are going to be looking at some real world scenario where we can pick a data set and then try to train a model, whether it's a regression or classification based model, using the k-nearest neighbor. And then from there, we are going to move on to different non-linear supervised learning methods, like the tree-based techniques, where we are going to see decision trees, we are going to see random forest, we are going to see the extreme gradient boosting algorithm, and then move on to cases like support vector machines and so on. Thank you guys, and keep following me for more tips in machine learning.